Okay, today's lesson's the last lesson, lesson number 9 of this electrical circuit stuff. Now, electricity, while it's very helpful to us, also it has some issues that we need to be aware of in terms of safety, because our nervous system also runs on electrical impulses. So we can, they can be interrupted. Also, because electrical energy is pretty easily converted into heat. And so, we remember, if you're looking at I squared R as our power thing and power loss, and so, it's I squared, which the current, which is fairly significant there, and so that power loss often ends up as heat. So the human body, for example, is quite variable in its resistance, depending on whether we're damped, just got out of the shower or out of the beach, or whether we're super dry, whether it's a humid day, all sorts of things. So this little table graphic shows you the effect on the human body of certain currents. So this is in milliamps, so it's not much in the way of amps as well. So all the way down from 1 milliamp that you can feel, all the way down to 500 milliamps, which is half an amp, which again could be quite serious. So even well before that, you get certain ones. So this one here, muscles paralysed. So if you grab something, then you won't be able to let it go because your muscles will be contracted. So that's the electricity interfering with our body's own electrical impulses. All right. So let's have a look at then an example of our body and what sort of currents might typically pass through it. So here's an example. Alright, so we've got a household supply. So household supply, always 240 volts. So whenever you read anything that says household, always 240. Person's feet are wet, low electrical resistance, could be fatal. Alright, so let's have a look. Example 1, so assuming the resistance of your body is 100,000 ohms, determine the current passing through the body if you touch the terminals of a 12,000 volt battery on a car. So current, we've got R and we've got V. So Ohm's law would tell us V equals IR. And so current times 100,000. So if we divide both sides by 100,000, so that would then be a current of 1.2 by 10 to the minus 5 amps. Sorry, made a little bit of error there on that one. It's not minus 5, it's minus 4 when I didn't count my decimal places properly. So 1.2 times minus 10 to the minus 4 amps. So minus 4, so that's 12 milliamps is what we would convert that to. And so when we have a look at that, here's 10 here, it says painful. So if you put your fingers on that, you probably feel a little bit of a zap. Alright, so let's have a look at another example. Alright, so for example though, this time on this example, we come out of the swimming pool and now our resistance of our body's only 1,000. So B equals, alright, IR, let's say the voltage is 12, current times 1,000, and so 0 divided by 1,000, 0.012 amps would be the current. I made another error over in that one, I'll go back to that one. So 0.12 amps is 12 milliamps for the current. Now, as I said, I made a mistake here. On this one, it's not right, I moved my decimal point the wrong way, I should have moved it this way. So it's 0.12 milliamps. Alright, so that one's 0.12, but this one's 12, so when we go back to our table, the 0.12, maybe you'll feel something, maybe you won't, but certainly the 12 milliamps is painful. So you would, if you're wet, feel that. Now, if you then look at this example, so instead of just a car battery, we're now touching 240 volts. B equals IR. So we're going to 240 equals the current times 1,000. And then when we do that, we get our current is 0.240 amps, which is 240 milliamps. And according to our table, down here somewhere, it's not going to be pretty. Alright, so while electricity is very useful to us and very handy, there's also some risks to it, so we need to be careful about what we're doing so that we're safe about it. Right, so what do we use? Well, we use things called fuses, although not so much fuses these days, but circuit breakers. Alright, so a fuse is just a bit of wire that if the current through it's too big it melts. A circuit breaker is an electromagnetic device, again, that if the current's too much it opens up. Alright, so why do we need to worry about the current? And remember, as I said before, heat. Right, we don't want things heating up. And remember, the energy, it's proportional to I squared, so the current down. So what do we have? Well, these days, and these are in graphic, these days we have a number of things. Alright, so our electricity's coming in here. Sometimes there's a fuse on the poles, and that's that one. Then you got a meter, because you want to charge you for stuff, electricity, so you get that before you get anything, you get charged. Then often there's another isolator that can turn it off, the electricity, before it gets into your meter box. Alright, then the first thing that comes into in the meter box is this thing here. And this thing here is our earth leakage protection, and we'll get on to earth leakage protection a little bit later. So I've actually gone to the earth wire and the fuses first in the notes. But essentially the earth, you've got current going in and current going out, and the earth leakage protection monitors them to make sure they're the same. If they're not, it switches off your power. Alright, so then what happens? Then you go through all your fuses, all your circuit breakers, and then your electricity heads off around to the various things in your house. There it is, in the things in the house. And electricity runs back to what's called the neutral bar, then heads out, and then of course you have an earth wire as well in there. So that's basically what our house looks like. So with all those things, they're designed so that people can't electrocute themselves, and also so that you don't get too much current and heat, and then houses burning down. Alright, so the earth wire and double insulation's the next bit in your notes there. So basically, your earth wire, so if you have an appliance, so here's an appliance, and you've got your electricity coming in your appliance, there's a switch there, goes there, and you've got your appliance which is doing some stuff, whatever it is, and then you've got your wire coming out. Now, what happens if in your appliance here something snaps off and touches the outside? Alright, so you know, something breaks and then you bring your finger in here and touch it, then you could get zapped. So what there is, and I shouldn't have drawn that bit in green, but anyway, but what there is there's another wire that's attached, and that wire gets attached to your the cabinet or the outside of your appliance, and what happens then is, because you have your fuse or your circuit breaker in here, when this, and of course you've got current here, so what happens if this has got something broken touching the sides, so instead of going through the whole circuit and then out there, that now the current flows around here like this. So what actually happens is that the current goes up, our fuse breaks, and then we've got no electricity running to that appliance, making it safe, and no one can hopefully then get electrocuted. Alright, now these days though that doesn't quite happen as much, because these days we have what's called some double insulation. And so double insulation, if we've got our, it's just like, you know, TVs, you know, printers, computers, a whole bunch of stuff, now double insulation. And basically what we've got here is we've got plastic. So we've got a plastic outer case, which is an insulator. So we have still our fuse, we've still got our switch on the thing, and we've still got our circuit, and then we've got it coming out. Now the thing here with our circuit, it's often a printed circuit. So there's, you know, no chance of loose wires. So no chance of loose wires. Then if there was, our outside of it's made of plastic anyway. So this is what they call double UV insulated. Alright, and so double insulated, as it suggests, two lots of insulation. So one of them is the plastic on the outside, and the other is our circuit here that's printed. Often might be covered in plastic or something itself. So if these things are going to break, then the whole thing's going to be pretty much inoperable anyway. So makes it safe. All right. So the last bit, and I mentioned that before, was our earth leakage protection. So essentially, our earth leakage protection, which is here, this is our ELP or whatever they call them these days. So what we've got is we've got current coming in. We've got current coming out. And then, whatever's happening, it's happening here around the house. So what should happen, of course, is that any current that comes in goes around, and because we're in a whole single circuit, there's lots of circuits in the house, but they all start and finish here. So the amount of current coming in and the amount of current going out should always be the same. So if for some reason there's some leakage and somehow or other some of that current's leaking out, it may not be enough to, say, blow a fuse, this earth leakage protection device is far more sensitive and it monitors that. And so current in should always equal our current out. And if it doesn't, then the earth leakage protection device cuts off the electricity to the house. And it does it very, very quickly, in a matter of milliseconds. All right. And earth leakage protection, proven to save lives. So in Victoria, they're mandatory, and in most other states as well. All right, so that's about it for safety. You may not have picked up on what all those blanks in the answers are from this, so don't forget, look at my notes on the website and you will find that. So you've got a problem set there, number 7 it says, and then there's some test revision, so the teacher and me will let you know when that will be. So again, don't forget, if there was something you're not sure about, make sure you ask.